Hello and welcome to Chapter 4. This is the chapter we'll be going over summary statistics. So in Chapter 4, we're going to go over different summary statistics. In the prior chapter, we went over stem plots and histograms to look at shape, location, spread of distribution. Now we're going to be using more numerical summaries for the similar purpose. So, summary statistics, what are the main ones? Well, these are the 3 M's that we talk about all the time: mean, median, and mode. Then we also go into spread, which we talked a little bit about the range and interquartile range, variance, and standard deviation. These are our summary statistics that we'll be going over. Shape summaries are seldomly used in practice. You don't hear a lot of times that there is an asymmetrical curve, or it has different types of kurtosis. They're not used very much. We normally use the mean, median, and mode with standard deviation to really talk about the data we're looking at. So before we begin, we got to go over some notations. We already went over one, which was our fancy italicized n, which is our sample size. Now we're going to add a few more to the list. So here's our illustrated data example where we have n equals 10. Our next one we're going to talk about is x, which is the variable that we're measuring, or the age of the subjects. This is where we say x equals the age variable. Next is x subscript I, where the value of the individual, or I, for the variable. An example of this would be x sub 1 equals 21. So as you can see, the very first number here was the first one. X subscript 2 is 42, shown here, all the way up to x subscript 10, which was 52. Next, we have sigma, capital sigma, which is denoted by this Greek letter, which looks like an E. Sigma is the sum of all values, or capital sigma is the sum of all values. So anytime you see the Greek letter capital sigma, it's the sum of all values. So if we say sigma x sub I, we want the sum of all x sub I values, the values of the individual of the variable we're looking at, which would be x subscript 1 plus x subscript 2 all the way to x subscript 10, which is the adding up all the data parts, which 21 plus 42 plus all the way to 52, which we get a value of 290. So if we wanted to add up all the values, you add up all the values. Straightforward. Moving on, we're going to talk about central location and the sample mean. We kind of talked about mean before. Many people have gone over mean. I'm going to be going over the more proper way of figuring out the mean. We can call this the arithmetic average. It's a traditional measure of the central location mean, the average of the central location. It's the sum of all values divided by n. The sum of all values divided by n, which is the total number in that data set or population. We refer to the mean as x bar. So here you go. Here is our formula for figuring out the arithmetic average, or the mean. So we have x bar is equal to 1 over n plus 1 x subscript 1 plus x subscript 2 all the way to x subscript n, which we denote as 1 over n times the sum, sigma, of n through I equals 1 through x subscript I. Don't let this boggle you down or confuse you. We all know how to do average. We've been doing it before. This is just more of the proper way to show it. Going into an example of this, say we have these 10 individuals selected at random, have the following ages, our data set previously shown. We note that n equals 10. The sum of all the averages equals 290. And if we were to put that in the formula we just saw, it would look like this, where we have our sum of x subscript I as 1 over 10, because this was 1 over n, so 1 over 10, times the sum total of 290, which is 29.0. Most of the time when we do this, we're just going to add up all the values, 290, and you're going to divide by 10. This is saying the same thing, just being a little bit more, we'll call it politically correct, right? Because this value would always be 290 over 1, and then when we cross these out, you get your 290 over 10, which is going to give you your value of 29.0, which we would write out as x bar equals 29. A visual representation of this, remember, the mean is the balancing point of a distribution. So here's our mean, x bar is the middle point of our distribution. So if we had this being our 5 to, I believe this was 52, the average would be about here. This is where the balancing point of this distribution would be at. That was a horrible 2, by the way. The use of sample means. So the sample mean is the value of the observation drawn at random from the sample can be used to predict the population mean. So if you were to draw a number at random, this would be, the mean would be the closest value to drawing any of those numbers at random. Once again, it's the average of all the values. So if you picked 5, between 5 to 29, there's a pretty big difference even at 52. But the other values will definitely get closer to it, and that's what the average is telling us, is about the center, the balancing point of that data set where we are. Right. What we just went over was the arithmetic average for a sample or a data set. If you wanted to do for the population mean, it's fairly similar. The term that we want to look at here is, instead of saying x bar, we use mu, or it kind of looks like a fancy u. We call that mu, mu. And this is when we start using for population mean. We can also sometimes refer to this as the expected value. We'll get more into sample versus population moving forward. This is just exposing you to it, but right now, takeaway parts here are x bar equaling the average and for a sample, and we have mu equaling the average for a population. Next, we're going to talk about the central location of the median. We already kind of talked about this in the previous chapter. The median is the middle value of the data set. The way you determine where the middle value is you find the depth of the middle value. You take the total number of data points you have, which is n, plus 1 divided by 2. When n is even, the average of the two values is straddled, and you have a depth of n plus 1 divided by 2. So for the 10 values listed below, we had a median depth of 10 plus 1 divided by 2, which equals 5.5, which would place that value between 27 and 28. I believe we went over this. And the way you find the value of the median, if it straddles between two numbers, is you average those two values out. You'd add 27 plus 28 divided by 2, and you're going to get 27.5 for your median. If your data set is odd, your median will land on an exact value, and that exact value it lands on is the median value. Here we go as an illustrated example. When we count out to 5.5, it goes here, as of course there's no number right here, so we average these two together and we get our median value of 27.5. More examples of medians. So here we have an example of our data set 2, 4, and 6. The median value here is 4. It's the middle value that has been shown. Another example, we have 2, 4, 6, 8. As you can see, this is odd and this one is even. So when it's even, take the total number, add 1 divided by 2. When we work that forward, you're going to see you're going to get 2.5, which is a value in between here. So you take 4 plus 6, divide by 2, and you get your median of 5. Next one, we have our data points of 6, 2, and 4. Median does not equal 2. Remember, one thing we definitely want to look at when we're looking at data is we really should always organize it. We should always order it first, because if it's like this and you try to pick the middle value, it is incorrect. The median is robust. What do I mean by this? The median is more resistant to skews and outliers than the mean. is more robust. So here we have a data set from low to high. Give you a second to look at it. And it has a mean of 1636. Here's the same data set with a data entry outlier, error outlier. This data set has, so here's the same data set, but here's where our entry error is, or we can call this a fat finger, or a human error, something that happens, something that we don't want to happen on our homework or exam. When you're copying stuff down, you don't want to put a wrong number because then it changes everything. Same data set, but with this fat finger there, it completely changes the mean. The mean went from 1636 to 2743, which is a big difference for a fat finger. However, the median is still 1614 in both data sets. This demonstrates the robustness of in the face of outliers. So even if there is an error or outliers, like we said, the median is more robust to it than the mean. The mean is taking that outlier or skewed data into consideration. So the median is a great way to describe where the middle value is. You might see this a lot, or at least I do currently, in Las Vegas with the housing market. A lot of times they report the median value of houses that just sold in a particular time frame, as houses can sell sometimes for very cheap to very expensive. So the very expensive ones could be outliers, and the median value would show you what more of the true value in certain markets are versus the average value, because if you're looking at houses between 100, 200,000, 300,000, 400,000, there's a big difference when you have certain houses that are like $2 million. It's going to be a complete outlier there. And this is where a median value has a very big role in showing probably more accurately where the market is versus a mean. Mode. So we talked about mode a little bit. The mode is the most commonly encountered value in the data set. So this data set has a mode of 7. As you can see, all the values are shown here. Mode is the most common encountered value. As you can see, 7 is the most common number shown. It came up 3 times. The frequency is 3 for the 7s. This data set has no mode. As you can see, every data point is unique and only appears once. The mode is useful in large data sets with a lot of repeating values. The effect of skew on mean, median, mode. So as we talked about in the previous chapter where we had these silhouettes of our data sets, this is showing how these two things come into play and why sometimes we don't necessarily say positive, negative skew or asymmetrical, because when we talk about the mean, median, mode, if they're all relatively in the same area, you're going to have a more symmetrical shape. If you have the mode, which is maybe less than the median and less than the mean, it's going to show more of a positive skew. And if you have the mean being less than the median and mode, then you'll have more of a negative skew. This is just showing how we use these summary statistics with numbers as opposed to outlining them and doing the silhouette and explain it that way. You can get that point across by just reporting the mean, median, and mode. So here we go into spread and quartiles, and I'm going to stop this video here and pick it up in the next one for part 2, where we'll go into the spread and quartiles and interquartile range and how to identify outliers. All right, I will see you all in the next video.